Professor Luis Costa from Aveiro University, Portugal. Professor Costa talks about the study of the gene of materials using impedance spectroscopy. You are the power.
Okay. Thank you, Mr. Chair. Good afternoon, everybody. First of all, I would like to thank the organizers of this symposium to invite me to come back to Morocco. It's always a pleasure to come back. The first time in Beni Mellal. I will present this talk, and I came from the University of Aveiro in Portugal. Here it is the campus of the university. I work in the physics department as a professor of physics, and this is a new university with about 45 years and about 15,000 students and 1,000 researchers and professors. I'm also integrated in this I3N research group that integrated 3 different universities. So here is the campus, a quite nice campus in a very, very nice city. Okay. So only to remember what was our discussing yesterday. Impedance spectroscopy is a quite useful technique to understand the materials. And today I will try to show you how with this technique, impedance spectroscopy, we can see the aging of materials. So, impedance spectroscopy is usually, as the name says, we measure this impedance, okay? That is a complex number with a real part and the imaginary part. Usually these 2 quantities are function of the frequency, of course, and function of the temperature. And this impedance spectroscopy can measure directly these quantities. Sometimes this information that you have in these real and imaginary parts of the impedance are not enough to produce a conclusion, and usually, or sometimes it's better to calculate the admittance, that is the inverse of this impedance, z exponents minus 1. Also a complex quantity with a real part and the imaginary part. And in some conditions you can calculate the permittivity. So these are macroscopic quantities, but I can calculate the intrinsic properties of the materials using this complex permittivity. And of course we have also a real part and the imaginary part. Of course these quantities are function of frequency and temperature. Sometimes we have not enough data or good data to make conclusion with this permittivity, and then you calculate the inverse that you call the modulus, in particular if you have materials with enough conductivity. But we can calculate these 4 different quantities: impedance, admittance, permittivity, or modulus. So I will show you two applications of aging, how we can see the aging of a material using impedance spectroscopy. I made this is a polylactic acid, a polymer, and I want to explore or to see how this material is degrading with time. The second is how to see how the cement is cured with time. And I use simply impedance spectroscopy, and I confirm these results with other techniques. So in the case of the polymer, I use this simple configuration, a parallel plate configuration. This we have a gold electrode, a second gold electrode, and we put the polymer, that is a film, a very thin film, about 100 microns, between these two plates, and I can see and calculate these four functions as a function of frequency and temperature, and during time. And we made this during about 1 month to see how this polymer is degraded with time. The second configuration is used to study the cure of the cement. Okay, this is more a degradation, and this is a cure of the cement. And we use this configuration with 2 electrodes, and we put the cement here inside this, and we calculate again. We use again the impedance spectroscopy, but in this case we do not control the temperature. In this case we control the temperature. In this case we do not. Why? Because the cement, it is when we put water in the cement, it is an exothermic reaction. You cannot control. If you change if you make the temperature constant, the cure of the cement will not correct. So in this case we control the temperature. In this case it's room temperature simply. So then we have different models. We have the different data. That is, we make the measurements with time, with temperature, and with frequency, and we make these diagrams, the Nyquist diagrams. That is, in this case, we use, for example, the imaginary part of permittivity as a function of the real part, to see what is the form, what is the shape of this graphic that you have here. If this is a circle, a perfect circle with the center in this X, we use the Debye model that is here. Okay, this is the low frequency permittivity, the dielectric constant. This is the I. This is we call the relaxation time. But in this kind of materials, this is not. We do not see this Debye model, and we use Cold model or Cold-Davidson model. So the Cold model, the difference is that this circle is not centered in the X; it is below the X, and we define this angle here. We call the depressed angle, this alpha. Okay, when this alpha is 0, we are exactly in this Debye model. If the shape of this Nyquist plot is not symmetric, we can use this new function called Davidson that is not symmetric, and we also define these parameters. When we look to this expression, this is the Debye model. Okay, it's very simple, and the difference between this one and this one, we have here an exponent, and this alpha exactly this alpha. So this alpha is the depression angle, and if alpha is close to zero, we are in this model. Okay, this expression is this expression, and the same for this Cold-Davidson model. So the results for PLA, polylactic acid. So we control the films in a container at relative humidity 78% and the constant temperature at 25 degrees. And then we can see how is the temperature as a function for a certain time. Okay, for example, 3 days. We can see the variation with temperature of the epsilon prime, the real part of the permittivity. In this case, we fix the frequency, and we are just saying how it happens when we change the temperature. So we are a cryostat, and we put the PLA films inside the cryostat to change the temperature. We sweep the frequency, and in this case we use this representation. Okay, that is the real part as a function of temperature, but I can do the reverse. I can fix the frequency to fix the temperature and to see what happens as a function of frequency. Well, we have the same information. So this is epsilon prime, this is epsilon double prime, that is the imaginary part, and we see here very clear peaks, and these peaks are a sign of a relaxation process. So we see that when the frequency increases, the peaks go to the right. Okay, so this is very low frequency, this is high frequency, and I can calculate exactly where are these peaks, and then then I can see for each temperature what is where is the peak, that is where is the relaxation frequency. Then we calculate these peaks, okay, and then we can use, for example, an Arrhenius, and we say that, okay, this relaxation frequency is something like that, okay, this proportional to the exponential, this activation energy. And so if you put in this in a logarithmic scale, this is a straight line with a slope that is proportional to the activation energy. So we can see that this is exactly a straight line. And in the case of polymers, we can decide what kind of relaxation do we have in this polymer. Is this alpha relaxation, beta relaxation, or gamma relaxation? These frequencies are very low, okay? So this means that it cannot be the gamma relaxation. It will be or alpha or beta relaxation. But for the alpha relaxation, we must be something like that, okay, not linear. Usually we have this VFT model to describe this alpha relaxation. This is a typical beta relaxation process, and when we calculate this activation energy, the values are typical of this beta relaxation, about 10 kilocalorie per mole. So this is what happened during time. Okay, we see the activation energy decreases, okay, in the first moment. This is due to the water, because we put these films are in constant humidity, so the water goes to the film. So this penetration provokes the spacing of the chains, and this activation energy in the first times decreases. Then in the second moment it increases, okay. This is the placement of the water in polar sites. And finally, the adaptation of the new polar function makes this small decrease of the activation energy. So we are here. You see the degradation of this polylactic acid film. So second experiment. This is we try with the cement. Okay, this is the type of cement. And we put inside, in this cement, we try to put polypyrrole particles, very, very, very small particles, about nanometers, 200 nanometers. This is the diameter of these nanoparticles of polypyrrole. We start with a ratio water cement about 0.4, that is normal for the industry. And then we want to see what happens during this cure of the cement. So this is how are presented the curves. This is the impedance real and imaginary part of impedance as a frequency for a given day and for a given and for that at room temperature. Okay. Here we have nothing interesting. We cannot see no peaks, nothing at all. So we don't know if there is or not any relaxation process. But when we invert this and you calculate the admittance, we can see one peak here in the imaginary part that corresponds to the inflection of this real part. So this is typically a relaxation process again. And if I use this representation, Nyquist plot, that is admittance imaginary part as a function of admittance real part, I see again this circle, and then I can see, in this case, the center of this circle is not here, okay? And I'm sure that this is not a Debye model, so I can use another model. We choose, this is again how it happens for different days, or for different moments, how the real part of the admittance changes with frequency, okay, at different moments. So this is the beginning, okay, and then we see how it changes during time. Also for the admittance imaginary part, we see these peaks, okay, these typic peaks that inform me that I have a relaxation process. So the peaks changes, the peak changes with the moment, also the time, during time, okay. So I make in the first moments it's important because it's very quickly. When I put cement with water in the first moments, the reaction is very quickly. So this changes quickly, and then I can see that with time, with the cement is drying and is curing during time, and I want to see what happens in these functions. So this is again called the Nyquist plot. Okay, I can see the circles, different circles for different moments. Okay, and I can see I always see this relaxation process, and then I can calculate, for example, where is the resonating frequency as a function of the time of cure. So here, for example, we see the evolution of the admittance real part as a function of time. This is about 1 month. So in the beginning it increases a little bit. This is due to the dissolution of ions. Then precipitation decreases. This is several days, okay? And then this is practically constant. That means that the cement is completely cured and we have a good material. So this is what happens with the angle. Or say I see this circle and I see this circle is not centered here. This is not a Debye model. That is there exists this angle alpha, the depressed angle, and I want to see what happens with this angle alpha as a function of time. In the beginning it increases, then it decreases, then it increases, okay? But we see this alpha usually is a measure of the heterogeneity of the system. When I have alpha close to 0, that is, if I am in the Debye process, the system must be homogeneous, and we must not have dipole interactions between different dipoles. So here I see that the angle decreases, so it starts at 35 and it decreases. This means that this point here is going up, so it's closing to the Debye model. That is that the cement is becoming more homogeneous with time, which is logic. Then here we are just seeing what happens with this angle, again with time, but this is the same curve, okay? This is the normal cement that we have. Here it's difficult to see, but it is what happens when we put these polypyrrole particles inside the cement. That is, when we do that, this angle changes a lot, and we have a cement that is more homogeneous because this angle is really smaller than this one. That is, we can see how this cure of the cement is going with time. So we can conclude with dielectric impedance spectroscopy. We can see this evolution. In this case of cement, we say the evolution of the curve of the cement. In the case of the polylactic acid, we can see the evolution of the degradation of the polymer. And we confirm this in the case of PLA, for example. We confirmed with measurements of molecular weight. We can see the degradation of the polymer, and the curves are quite similar to these ones that we obtain with impedance spectroscopy. So then we can see what happens with we made the measurements of the contact angle with the camera. This is a water drop that goes to this cement, and we calculate this angle. But what is interesting, we see here what happens when this red curve, this is without polypyrrole. After about 4 seconds, this drop disappears in the cement. So the cement is not impermeable. So we lose completely this drop about 4 seconds. And when we put only 1% of this conducting polymer, we can see it. So the curve is similar, but we must wait about 36 seconds to see the disappearing of this drop in the surface of the cement. So probably you can use this additive to see to improve the quality of the cement. Of course, the cement is a quite complicated material. We use pure cement, but in the construction they mix cement with rocks and sand, and so things are quite difficult. And probably the curves that we see, they are not so nice. Okay, I want to thank this project and these entities, and also my students. Yesterday I finished my talk with a mistake, because I used the Google Translator to translate "thanks for your attention" to Arabic. And this is copy-paste of the result of Google Translator. And yesterday I understood this is completely a mistake. It is stupid. So, but today I make exactly the same. But next year, I promise, I ask to somebody, to our colleagues from Morocco, to write me this last slide. Okay. This finally, now it is really final. I would like to dedicate the next slide, the last one, to my friends from Morocco, because next June and July we have the World Cup in football, and we are in the same group. Okay, we have Portugal, Spain, Morocco, and Iran. Okay, then next slide is quite important, because it's the final standing of this group. I saw this. Okay, I am sure this is true, but we must be careful. I show you why. Okay, this is the final standing. Portugal first, of course. Morocco second. These two teams will pass to the next one. Okay. No, I don't think. No. I'm sure. No. Probably it can be, but we have a problem. The problem is this guy you see here. Okay. This guy, and this is one of these last goals in 15 days ago. So I think if you want to change these teams, you must be really careful with this guy. Okay, thank you very much.
Thank you very much, Professor Costa, for your important presentation. If you want to come questions tape. Des questions?
Thank you. See you in the Mondial. And my question really about the cement. Why is it not wise to control temperature? Normally.
In the case of the cement?
Yes.
Because in the case of the polylactic acid, we control the temperature. So we make a measurement. So we fix the temperature, we sweep the frequency, then we change the temperature and so on, okay? It's normal, this is impedance spectroscopy. But in the case of cement, if I try to fix the temperature, so as the cement, when I put water in the cement, it's a very exothermic reaction. If I try to control this, so the temperature increases, if I try to control this temperature, the cure of the cement is completely destroyed. So I see in the cement cracks everywhere because the temperature must increase and then decrease, okay, to have a real cure of the cement. That's why we try to do this. Okay, room temperature. What happens? Okay, and you know that in fact the temperature changes, of course, but we see, for example, in the first moments, the conductivity increases because epsilon double prime increases, but this is due also to the temperature that changes. Okay, everything is changing, temperature, and this has consequences in the other parameters, of course.
I think I'm not suggesting to cool it. I'm suggesting to control temperature. Maybe, for instance, at 40, at 35. Just to make sure that everything is under control.
Yes, I agree, but if imagine I have a cement, I put water, room temperature.
No, I'm not saying that, sorry. You control it from outside. You can make a thermostat.
Yes, I can do that, but then I am fixing the temperature. Yes. I am trying to put a constant temperature, and the cement doesn't like. Okay? The cement wants to increase.
I disagree with that.
Yeah?
Normally when we build homes, in winter time, the cement gets much better than in summertime.
Yes, but when we make the cement, even the temperature is low. When we put the water, the temperature increases.
Yeah.
So you can do that
exactly
from 40 to 50 or minus 10 to 0, but it always increases. That's why we don't try to force it. I put this problem because we made this work with the industrial society, and I said that now I make impedance spectroscopy, so I know that the temperature must be constant to make a measurement to know what is happening. And they say no. I sell the cement. I want to know what happens to the cement. Okay, that's the problem. Practical, yes, purely practical. Okay.
Another question.
I have a question regarding the PLA. Thank you. As you know, aging depends on which state your polymer in the initial state of your polymer. So it's out of equilibrium structure, and it will try to reach an equilibrium with time. So my question is, how did you prepare your polymer film? Is it semi-crystalline polymer or it's amorphous?
Yes, I did not prepare it. This was also prepared in collaboration with the French colleagues from CNRS. So they are polymerists, and they know how to do that exactly. But I'm sure that's true.
Yeah, I mean, did you look for the structure, for example, or the mechanical properties, and you see they are degrading with time?
No, we saw only by molecular weight. Yes, and studying water vapor permeability. Okay, see what happens to the permeability of the film with time. Okay.
I have a question dealing with the measurements, or more precisely about the cells. The cells you use to make your measurements. So you use a planar structure in the case of polymers,
yes.
And you use a kind of a reactor with electrodes. It's because of technical, I suppose.
Yes,
technical. To spin the cement or something like this. Yeah?
Yes, because usually you make measurements with the parallel plate capacitors. It's easier. We know all the expressions, okay? But in the case of cement, it's not possible, or it's difficult. So we can, of course, we try with that, but we have the same results. But the question of the practical questions from the society, they have containers, cylindrical containers, so we put these electrodes. And we can calculate also, if you measure the impedance, but you can calculate even the permittivity, even if you have this configuration with these electrodes in this cylindrical container, we can do that.
And how do you manage to extract your permittivity? Because you don't have a uniform electrical field, so I suppose that you have measurements of capacitance.
Yes. Yes.
And to extract your
yes.
your permittivity,
yes.
you have to take account.
No, I can measure in the case of parallel plate configuration.
Yeah,
it's easy. I can.
It's easy, but
it's easy.
In the other case.
In the other case, there are expressions. Right? There are theoretical expressions that you can also calculate. So there are more complicated expressions that depend the distance of the electrodes, the diameter of the electrodes, the weight of cement that you have. Okay, there are several, but there are some expressions that can use it.
Okay.
Also.
Thank you.